Welcome to another RDWorks Learning Lab. Well, I've returned from my laser rehab in St Lucia, and I'm not sure that it's done too much good. I feel sure that I've wasted a lot of the kids' inheritance. But on the other hand, maybe it did, and I'll go back and try it again next year. In the meantime, we're going to talk lasers. Today is going to be a bit of a strange session because I'm going to offer you guys a challenge, especially those that are about to receive their high resolution compound engraving lens. Now, I'm going to set you guys something that I call the Checkerboard challenge, and it'll be pretty obvious why it's called that when you see the pattern that I want you to try and achieve. Now, if you happen to have an Epilogue or a Universal or a Trotec machine, you're welcome to join in, because I would really like to see what the dotting capability of your system is. Not the speed, but whether or not it's capable of producing good quality dots on my checker pattern. Now, I'm fairly confident that you guys with the big machines will be able to achieve it, and reasonably fast. I had a light bulb moment a couple of months ago, and I quickly rushed out to my workshop here, set up the machine, and realised that my idea was crap. I've been in rehab, and I've had plenty of time to sit down and do nothing except sip champagne, float around in a lovely warm pool, and think about laser machines. And this problem kept on crossing my mind. And all of a sudden, I thought I must give it another go, because I don't think I gave that light bulb moment that I had a few months ago a fair crack of the whip. So we're going to approach it in a slightly more methodical way rather than an excited whoopee eureka moment way. And today we may fail again. Sorry, not we, I may fail again. But it'll be a public failure. But we shall know that it's not possible to get anywhere near what the big boys can do. But at least it's good to know. Now, as with all my testing, we need to set a standard somewhere so that as we move on we can compare whether or not we're improving. Whether or not it's going to work, we can't say, but at least the idea was genius. Now, you're all familiar with my little dot dash focus setting and checking procedure for setting up the focus. Well, here is that same thing, but about 10 times harder. The pixels and the spaces are all 0.1. The line spacing this way is 0.1 because they're square pixels. If you can reproduce this on your machine, it will be a miracle, unless you happen to have a compound lens, or maybe you might get close to it with a 1.5 inch lens. The next question is, what material are you going to use? Because the material that you use for producing this pattern can have a significant effect. It can be anything from glass to your mother-in-law's slippers. Now, in the text under this video, I will put a couple of sources where you can go to download this pattern, and if you want, you can download my RD file that I've already prepared for it. But I will show you how I went about preparing the pattern. But we need to set it to scan. Now, I've got a speed set here of 150 millimeters a second, because I happen to know that this machine can actually work that fast with dots this small. Now, that was a real surprise to me, but we'll talk about that after we've seen the results. We're going to set it into scan mode, and we're going to set the power very low. This is a 60 watt tube, and 13% might be a bit high. I think probably I got my best results when I was probably down at around about 10 or 11%. And that is right in the middle of the pre-ionization zone for this machine. It starts at about 8.5% and runs through to about 14%. So I'm not in the steady pulse region for this machine doing this test. Now the other important thing is, it's going to take twice as long, but to make sure I get the maximum accuracy, because it's a very fine pattern and I want to see the 0.1 resolution between these dots, I want to see the diagonal lines. And if I use X swing and I've got offset between the two lines, it will confuse the pattern. So I've set this to X unilateral, which means I shall only scan one way. But that will ensure that I get the correct relativity between these lines, and I should be able to retain this pattern. This is a 254 ppi picture. So I've got to set the interval to produce 254 dpi. And that means, because these pixels are 0.1, I would expect to set an interval of 0.1. But you'll notice I've got an interval set here at 0.099. I can't explain why, but what I will do, I will set the interval to 0.1 for you. Okay. And then we'll go and have a quick look at the preview mode. And here we are. All these are signals, dots, which are going to occur. And all of a sudden, you see yourself, hang on, I've got first row, second row in, third row out, fourth row in, third row. They all go in and out because we've got a checker pattern. But look at this row here. These are parallel. They're lined up. We've got another set just here. We've got two rows that are not in sequence. There's some sort of aliasing taking place as RDWorks scans my image. It's not scanning it correctly. And so consequently, what I had to do was to go back and do a little bit of an experimentation, and I found that if I set the interval to 0.099, in other words, it's 1/100 of a millimetre smaller than the supposed pitch, and I now check out the pattern, it's perfect. There's some sort of, as I said, scanning calculation problem within RDWorks that causes this issue. But this at 0.99 gives me a perfect scan. This is not a screen presentation problem of aliasing. This is actually the information that's going to go to the machine to drive the stepper motors and the laser tube. I'm going to set this down to as low as 10%, which is just on the threshold, just above the threshold of firing for my tube. Well, several people have asked me what the compound lens is like for cutting. I'm just going to make a special focus gauge here for the compound lens, and I'm making it from what looks like 5mm acrylic. I'm running this at a speed of 10mm a second, and I've got 65% power. I think I've probably got too much power there, or not enough speed, but hey, this was a guess. It's self-illuminating acrylic, so it shows up the numbers extremely well, and it runs from 10mm here, 0.1, 0.2, 0.3, 0.4, all the way up to 11 and 12. So it's a very short range of focus, so I can very accurately set to 0.1 of a millimetre now, anywhere between 12 and 10mm. Now the compound lens has got a nominal focus range of around about 10.5 to probably 11.5, depending on the power and the speed that you run it at and the material that you're using. So the focus is not necessarily a fixed point. So we'll try setting the focus with my dot test as usual. So that's 11.3. I'd say that's probably about 10.8, maybe 10.9. Now here's what 10.3 focus looks like. Now this is pretty good really, because look, you can see we've burnt holes right through the paper here, but those holes are equidistant apart, so we've got at least 0.1 burns through there. And look at all these, we've got holes through the paper, and we've got a burn mark without a burn. We've eroded the paper. It hasn't evaporated, we've burnt that paper away without burning it. And here we can see just a little bit of the carbon that's left behind. And we've gone right through the paper here. But look, again, we've put virtually no halo around the lines. This is at 10.3. Now what happened when we went up to 11.2? That's pretty amazing, isn't it? Look at the thickness of those lines. There. I haven't got a measuring piece of equipment with me, but they're definitely around about less than 0.1. They're probably something like 0.05, the thickness of those lines, because look, the pitch between these is 0.1. So if the pitch between these is 0.1, I could probably get 2 or 3 of those lines between the centre of these dots. So they're miraculously thin, those lines. And then when we went to slightly different, we went to 11.5, only about 0.2 difference. More or less the same. So it looks as though we should be focusing this up round about somewhere between 11 and 11.5. So let's go and have a look to see what happens when we run the checker pattern. We're going to run this first test at 150 millimeters a second and 10% power. That's a very small amount of energy per dot, considering this is a 254 resolution image. We've got all our nice diagonal lines down here. So that means we've got no offset between these lines. They're all starting up nicely. We've got comfortably 0.1 gaps between these 0.1 dots. But the other thing that you'll notice is we've got gaps this way. Our lines are a lot thinner than 0.1 because we're running so fast. We're painting thin lines. That's on a piece of paper. I think we might be able to do even better than that on a piece of black anodized aluminium. Same settings as the paper, 150 millimeters a second and 10% power. Well, again, not bad. I mean, we've actually got lines rather than dots, because that's what the machine is actually outputting. I mean, what that means is I could probably go faster, because to see a line means the power has come up, drawn a line and dropped down again. Whereas if I only see a dot, it means I've come up, just about made the power and dropped straight down again. So actually this is remarkable. I'll have to do a quick calculation in a minute and find out how fast the power supply is running to be able to do that. Wow, running 20% faster. It's lost a little bit in places, but you know, for running at 200 millimeters a second, that is a pretty good pattern. It's about 11.4, 11.5, so we'll try this now. This is my laser tile. Same settings, 200 millimeters a second and 10% power. Now I don't expect it to make a mark on here because I think we need a little bit more power. Well, it's a bit faint, but we'll go and look at that under the scope. I mean, that's not bad. I mean, these marks here are interference with some of the dots that are in the background, because this is not a brand new clean tile. As you can see up here, look, there's all sorts of little odd dots. I chose a fairly clean area to test it in. Yeah, the dots are not very uniformly black, but they're all there, but they're not really solid. So the only way that I can test this would probably be to either slow the speed down or maybe increase the power just a shade. Actually, that looks nice and black, doesn't it? Well, again, I think that's a pretty fair result. That would give a very good picture. So these are definitely less than 0.1 dots. We've got space between them this way a little bit, but I mean, you can see clearly that we've got our
lines here to indicate that we've got our checker pattern there. We could try it on wood to see whether or not we can get any satisfactory result on wood. I mean, obviously what the problem is here is we've got different colours depending on the resin and the composition of the wood, because you can see the banding is running up with the banding in the background, the grain. But the essence of it is we've still got our 0.1 or less dots. Now, might be able to improve that by increasing the power per dot. How could we do that? I think I'd rather slow it down rather than increase the power. The quickest way to double the power is to halve the speed. And halving the speed will also make the dots a little bit bigger as well. So let's try that. And immediately you can see the colour difference. We've still got our 0.1 dots if we look here, but we've also got some murkiness where we've got this banding. We've got all sorts of strange things happening here as we get various chemicals building up in the dots. So wood is not a very good material to work with generally. Certainly it's not uniform like the other materials that we've been working with. Now, to be fair to this Beermat card, I ought to put the speed back up to where it was before, 200. And that is a mixture of burn and a bit of no burn. But even so, we've still got our 0.1 dots there. We've just got to get them a little bit blacker. We'll have to do that with probably increasing the power a shade. Okay, so there we are again. A nice regular set of 0.1 or better dots. Now I'm just going to scribble for a minute because I am interested in the response time of my power supply. We started off this exercise maybe 6 or 9 months ago thinking that my power supply was probably somewhere in the region of about 3 milliseconds response time. Then as I've worked up with finer and finer dots, I found that for some reason or other I can produce power faster and faster. So now we've arrived at the compound lens and really super crisp sharp dots. We want the shortest period of time that we can possibly get to produce a nice clean dot. Now the shorter the time, the faster we can go. And I've reached a point now where it looks as though I can go at something like about 200 millimeters a second. Bear in mind the resolution of this pattern is 254 dpi. That's a dot size of 0.1 millimeters. And I'm running at 200 millimeters a second. Now the maths in this are not particularly difficult, because if I take 1 second and divide it by 200 millimeters, I will find out how long it takes to travel 1 millimeter. It was 0.005 seconds. That is 5 milliseconds. Now if we look here, we've got dots that are being put down at the rate of 0.1 millimeters per dot. So there are 10 dots per millimeter. How long does it take to produce a dot? Well, the answer is 5 milliseconds divided by 10 dots, which equals 0.5 milliseconds per dot. Now, as we've talked about before, the general specification for a power supply for these machines claims to say you can achieve 90% of the required power that you ask the power supply to deliver in less than 1 millisecond. So my power supply at half a millisecond is twice as good as the promised specification, which is why I can get 254 dots per inch at 200 millimeters a second. I probably could get more, perhaps with aluminium, which is the most sensitive material, it's worth a try, seeing if we can get up to 400 millimeters a second. We were previously running aluminium at about 10% power. So now we've got it at 12% power, but we're running very, very fast at 400 millimeters a second. I have to say that I'm amazed by that. I don't know about you. 400 millimeters a second, 254 pixels per inch. Okay, well what you've just seen me there do is to run this system with a response speed from my power supply of about 0.25, quarter of a millisecond per dot. That's something I never imagined I would ever see on a cheap Chinese machine like this. This has just got an ordinary MYJG bottom of the range power supply. It's an A grade power supply rather than a B grade power supply, which most of you guys have got if you bought them off of eBay. This is pretty remarkable, and it actually makes me wonder whether it's worth proceeding with the planned program today. Okay, I'm going to, because it's sufficiently interesting that I would like to find out the answer. As I said, I've theorised on the answer as to whether or not we can run even faster than this and produce good dots by using a completely different technique, much more of the technique that they tend to use on the RF tubes. Now, the RF tubes are a wonderful device. They're expensive, but they have one great advantage over our system here. Now, you've seen this little sketch many times before, and as I've described to you, there are only two lines from the controller that make our laser tube work. There are only two lines from the controller that make an RF tube work. So what's the difference between ours and the expensive piece of kit? Well, the answer is it lies in this power supply unit here. This red line here is an electronically controlled circuit in here for controlling the current passing through the tube, and that works at electronic circuit speeds. Let's call it microseconds. It could even be nanoseconds, but it's probably 1,000 times faster than what happens in this blue line, which is working in millisecond timescales. When we tell the tube to switch on, the first thing that has to happen, we have to charge up a transformer in here with a magnetic field. And then his electronic switch in there turns the electronic field off. And that induces a very, very high voltage here and allows the tube to fire. But this circuit here has to keep going. So it has to keep charging up and discharging, charging up and discharging. It's the charge up time that's the thing that really slows the system down. Because this is basically an induction system in here, very much like the sparking coil in your car. So there's a finite speed at which this thing can run. And I'm remarkably surprised at the results I've just had. But nonetheless, we're still working in millisecond timescales as opposed to microsecond timescales for this red line. Whereas a RF tube has none of this problem here. It has a separate power supply which is pre-charged up to this voltage that we want, so that as soon as this line switches, it allows that charge to go into the tube, and the tube instantly switches on or off. But the fact that it can switch on and off instantly basically means it can run much, much faster than our system here. Now, that means we get extremely good control of the power per pulse or power per dot, and the speed per dot. So this RF system is absolutely unbeatable for excellent engraving, photo dot engraving. When it comes to cutting, this good old China blue and all your machines out there are on a par. It just needs raw power to bash through materials. I'm slightly exaggerating, but the essence of it is the only serious advantage of an RF tube is its control of power for superb engraving quality. We've already had some superb engraving quality off this machine, but it's been done slowly. And my goal was to say, well, can we get any closer to what an RF tube can do? We're limited by this line here, the speed of this line. Now, here's the pattern that we've just done. And here is what happens to that red and that blue line as we produce this pattern. So on the first line of the pattern here, we set the power to 10% or whatever. And as soon as the cycle started, the power sat there at 10%. And then we started off with the first dot. And the first dot came along and it said, we need to switch on. And I know these signals are going upside down, but that doesn't make any difference. It is the way that this system works. On a low, it switches the power on. So as it switches on and goes towards 0 volts, it allows the beam to transmit power. And then it switches off. And we get a white space. And then it switches on and off and on and off and on and off, and hence what we've got here. So we get a single scan of on-offs, and then we turn round and we come back for the second line, and then we turn round and come back for the third line, etc., etc. And eventually, when we've finished the pattern, the red line drops back to 0. So that's what I would class as normal engraving, what you've seen us do today. And that means we are limited by this switch on capability. Because although we've switched the power on here with this blue line, and it can do that extremely quickly between the controller and the power supply, and that's what that blue line is. The blue line is this switching line here, which is quick. The thing that isn't quick is what happens between that blue line and the laser tube. Okay, well, here we are in Photoshop, and I'm going to just quickly go through another form of engraving, and this is 3D engraving, where we employ a system called Grayscale. And let me quickly go through what that means. We start off with a coloured picture, and normally we'd send this coloured picture directly into RDWorks, and when it comes into RDWorks, it looks like that. It's already had all the colour stripped away from it. And I can do the same thing here in Photoshop, and I want to stay in Photoshop for a moment because I want to show you something. Want to discard the colour? Of course I do. And there we go. So we've got the same image here in Photoshop now. It's something called a grayscale image. And we shall find the pixels in here are not what they seem. We've got white pixels, we've got various shades of grey pixels, and we've got black pixels. And this coloration is done in accordance with a very special scaling system called the Grayscale system. Okay, so we've got all these various shades of grey hiding in this picture. And I can go and have a look at the ratio of these different shades with this scaling system that I've been given here. It tells me what the various amount of different levels are. Now the level here at this end is black, and it says, well, you haven't got anything really black. You've got a little bit of black in there, but you've got lots of very, very dark grey, and then you've got lots of mid grey, but you haven't got very much white at all at this end. Now the grayscale runs within two numbers. 0 represents absolute blackness, and the number 255 represents pure white. So between these two numbers, 0 and 255, we've got 256 colours that we can use to paint this picture. When this picture has been brought into RDWorks, as I said, all the colour has automatically been stripped away, but nothing has changed about this picture from what you saw in Photoshop. We've still got all the same levels of grey, white and black in this picture. And if we bring up the bitmap handle, we shall see that it's a picture with 72 pixels per inch. It's not a very high quality picture. And you can see the pixels there. Now, you would not attempt normally to try and reproduce this picture in grayscale, because although you can produce different shades of brown on wood, for example, you can go from a darkish brown to a slight scorch. The temperature difference between producing those colours is so small that you find it almost impossible to get a good colour range. And of course, grayscale is no good to at all on something like this material, black anodised aluminium, because there are only two colours in here, black and white. So you can't get any shade of grey in there by varying the power. You only get black and white. And so consequently, normally with a picture like this, you go to the next process, which is to say we're going to set the image density, let's leave it at 72, and we're going to dither it, and we're going to do it with dots. Apply to view, yes. Okay, now it doesn't look any different, but this is what we've been doing earlier with our checker pattern. Look, this picture has now been converted into black dots and white spaces. Now that makes it very simple for the computer to interpret. Okay, so we've now got our grayscale picture, which you can see here, look, in RDWorks. And what happens if we send that straight to the machine now? We don't dither it. Well, the answer is we should get a black and white picture. Now that doesn't look like a black and white picture. Anything that's white on here means the laser is switched on. So the tube is switched on. So this picture is basically a negative. But what it means is we've only got two colours in this picture. So the controller has said anything with a colour 128 and above, make it white. And anything with a colour 127 down to 0, make it black. So it's automatically converted this picture into a black and white picture. So what other options have we got to work with grayscale? Because we use grayscale for 3D engraving. And how does that work? Well, it works like this. This will not engrave as a 3D image because it isn't the right sort of image, but I can use it to demonstrate the principles. What we do, we go into this bitmap and we specify a minimum value, and let's make it 10 power, and a maximum value, and let's make it 80% power. Okay, and we will then say fine. What that really means is anything that is white, we're going to use 10% as the minimum power attached to white. And anything that's black is going to be given the high power, 80. So 80 is going to burn black and 10 is going to burn white. And any other shade in between on this grayscale image is going to proportionately be the power in between here. So let's just see what happens when we put that information into here, and we'll take a look at the output. No different. It's got a different colour, but we've still got a black and white output. There's a good reason for that, and that is lying in these parameters. We've got a switch in here called output direct. And that allows us to convert this picture in a completely different way. This output direct changes the way in which the controller works. Let's take a look at what the output is now going to look like. Aha! How did that happen? Back to the drawing board. Now, you remember with normal engraving, the power was constant, and all we did was to switch the power on and off so that we got black dots on a white background, or whatever colour background happens to be there. But this was a dot producing mechanism, and it came about from this red and these blue lines. The blue line was switching on and off, and the red line preset the power. So when you tick that output direct box, this is still a switch and this is still a power line. Nothing happens except that these perform a different dance. What happens now is this beam switches on at the beginning of a scanning stroke, and then the Grayscale decides that it wants to print a black area, so it puts some power on, and then it produces a grey area, and then a slightly darker grey area, and it gradually gets white all the way down to here. Look, nearly white, nearly black. And so as the picture scans across, for every pixel, instead of the pixels switching on and off like this, if they're all different shades of grey, then the power adjusts up and down to produce those different burn characteristics and produce the different shades of grey. Now, as I said to you, you can't actually easily, although so many people have tried it, produce a Grayscale picture in this way. But what you can do is you can use this power. Now, I can't put my hands on a good example at the moment, but here's a crude example which will describe what we're talking about. This has been 3D engraved. As the power gets high, so the deep right, so as the power builds up to a black level, we get a deep cut, and when it's a white level, we get a shallow cut. So we can do 3D engraving by changing the power level as we scan across this picture, like this. And so every scan that we go across, and the blue line is now switching on the scan and switching off the scan, switching on the scan and switching off the scan. So it's now only, instead of switching on and off dots, it's switching on and off the power at the beginning and the end of each scan line. And during the scan, the power is moving up and down to burn different depths into the material. And that's how we get 3D engraving. Okay, I hear you say, so what's all this got to do with running the machine faster for dotting? Because with dotting, we've only got black and white. Well, the great advantage of this system here, Grayscale engraving, is that with the blue line, which is operating the switch on and off of the tube, it works in millisecond timescales. The red line is operating in microsecond timescales, so it's able to change the power in this tube extremely quickly, whereas the blue line is only able to turn on and off relatively slowly. It doesn't matter that the blue line turns on and off slowly when we're doing Grayscale engraving, because all it's doing is saying, right, we're ready to start, and then it stays on, and then it switches off, then it stays on. So we've only got one sluggish opportunity at the end of every stroke. But of course, remember, at the end of the stroke, you finish cutting, and then the head has to slow down and it has to turn round and come back. And before it starts cutting, the beam has switched on. So it doesn't matter that it takes a millisecond to switch the beam on. But once the beam is on, the power starts coming in and out at an incredibly rapid speed. So we have the ability to produce all this wonderful different depth of cut at very high speed. Really, it would be great if we could make our dots somehow happen on the red line as opposed to the blue line. If we could make our dots appear in microsecond timescales as opposed to millisecond timescales, wow, we could get pretty close to probably what the big boys' toys do. There is one major problem with this system. Once the tube is switched on at this blue point here, it can operate extremely quickly between different power levels. The only problem is, if ever it sees 255, and you remember what 255 is? White. And what happens when we see white? We switch off. So every time we see white in this 3D engraving, the power will switch off and we shall get a sluggish start again right in the middle of our very high speed operation. All of a sudden I thought, well, hang on, we don't ever have to show the grayscale white. Let me show you the trick that I saw. Now we shall either need Photoshop or some sort of photo manipulation program to carry out this next tricky task. Now here we've got our dithered picture, which, as I said, is it's a two-colour picture, black and white. And we would normally have to use that without the switch on, and that would give us black dots on a white background. If we tried to use that with the switch on as a grayscale image, what would happen is we would print black, but every time we came across white, the tube would switch off, and there would be no advantage to us at all. We may as well just have the blue switch turning on and off. But if we perform a silly trick like this, we've got our image, and we'll save that image because it is a bitmap. And if you look, the colour depth is 1 bit, i.e. just black and white. Okay. We'll load the dithered bitmap back in, and there it is. And now I'm going to go to Image, Mode, and I'm going to turn it into a grayscale. You see, I haven't turned it into grayscale at all. It's still dots. It's still black pixels. It might look like a grayscale picture on the surface there, but in reality it's not. But we can now turn it into a grayscale picture by setting the levels. Select Layer. Now if we take a look here, you'll see that we've got a lot of black, a lot of white, and nothing in between. I could set the output levels, and let's play with this for a minute. Look, if I set the output level to 150, 150, look what happens. I've got black and grey. If I say OK now, and I go back in and check the levels, look, I haven't got any white anymore. I've got black and a mid-grey. Now what I'm going to do is play this game a little bit slyly, because what we're going to do, we're going to set the output levels instead of grey, which I did purposely to show you what's happening. I'm going to set the grey level to 250. There we go. So let's bring my tiger in again, and we can see that it is a bitmap, and it is only black dots on a white background. We'll now go into image mode. We'll set this as a grayscale picture. OK. And if we now go and look at the levels, image adjustment levels, we'll clearly see that it shows us that we've only got two levels in this. We've got black and we've got white. But we can fiddle now. We can cheat. We can make this white level, we want the output levels of this picture to run between 0, which is black, and white, which is not quite white, if it's 250. So when the controller sees this white background now, it's not sufficiently white to switch the machine off. So what we're really doing, we're using grayscale now as a selective black and nearly white image to get us into this speedy mode of operation. So now I will save this file as a bitmap, 250 TIG save. So this time we'll go into RDWorks, we'll delete that one, and we will import. We've got what looks like a bitmap, but we know it's not a bitmap anymore. It's actually a grayscale picture, which means that we can use this switch here, output direct. OK, and let's see what the picture is likely to look like. It's a dithered grayscale bitmap where there's only two levels of grey in there, nearly white and black. Now the problem that we've got is working out what these values here are going to be. Now I'm going to mess here with the max power for a minute, and I'm going to set the max power to maybe 13, and if I press the pulse button, beep, I can see that I've produced a little black dot, 13% power, with just the sharpest pulse. Now what I've got to do, I've now got to change the power down, max power, to, let's just try 9. Now I'm going to do the same thing again, a quick, let's move it. I'm going to move it along and do a quick pulse. And I've still made a mark. So that's no good. So let me take it down to 8. Now this is where I went wrong the last time when I jumped in and tried to experiment with this. I just chose a couple of random values and the results were rubbish. And it was only when I was relaxing in the pool that I realised how stupid I was. And we do another pulse. I can just see a little puff of smoke, so that's no good. And that was at 8. Try again. Pulse. No mark. I didn't see a little puff of smoke. Now, if I hold the pulse button on longer, can I produce a mark? If I can, it shows that I've still got power there, but it's very, very low. Pulse. No, I can't produce any burning effect at 7. So let's creep up gradually. Let's go to 7.8. Pulse. Oh, just the merest hint of a puff of smoke there. I can see just the merest hint of something there. I don't think it'll be regarded as a mark. We could try 7.7 and see what happens. No puff of smoke. Let's hold it on. Yes, I can get a burn. So I've found that threshold. Well, it's not a stunning success, but it's not an abject failure, I have to say. That is you know, a few months ago I would have been really very happy with that as one of my pictures. There is not any real hint of 3D-ness on there either, I have to say. There's just this banding here, there's just a little teeny weeny hint of, you know, a wrinkle round his neck like there is round my neck. There's a reasonable amount of detail here on his whiskers. You can see some of the hairs round here in his ears. We need to stand that beside the same thing done with just a dithered picture. Now this is not going to have a huge amount of detail in it because this has been scaled up from 72 dots per inch up to 254, and you can't invent detail. But we can take a look here at things like the whiskers down at the bottom here, and look, you can see very clearly that we've got much better definition in things like this. You know, all the hairs here, the hairs in the ear, I mean, you can actually count the hairs around the edge of the ear there where it's a little bit fuzzy here. Generally, without a shadow of a doubt, this one's crisper than that one. But, I mean, it was either going to be an absolute stunner, better than this, or not work at all. The last time I tried it, it was just a brown piece of paper. So I think it just proves again that what we can do with the compound lens is to get absolutely certain we can get 0.1 dots and probably less than 0.1 dots. And, you know, 254 dots per inch is a pretty good resolution picture, especially if you get a high quality image to start with that you can downscale. Well, although it was a good idea, I think we have to admit that 600 millimeters a second for this one and 200 millimeters a second for this one, we're going to have to take the slow road if we want quality on these Chinese machines. We're going to have to leave the high speed, high quality to the big boys. We can go for slow speed, high quality. If you want to make one of these high resolution focus gauges and you want to play with the checker pattern, take a look at the text below this video and I will tell you a couple of sites where you can download them. Or you can write to me directly, as you have done in the past, and I will send them to you by email. Well, thanks again for your time, and we'll catch up with you in the next session.